Let us start this lecture with a thought process from Abraham Lincoln. He says, when I do good, I feel good. When I do bad, I feel bad. That is my religion. It's a very great thought, and similar thoughts are also there in our scriptures, and which you may not be aware as such, but it is important thing to ponder. And let us now get into our discussion on the thermodynamics. And in the last lecture, if you look at, I started with the defining a pure substance, right, and we looked at the definition of pure substance, which will be having uniform chemical composition, right, and we also look at the phase change processes. And we started taking the water as a pure substance as an example, and then we keep the temperature constant and look at what is happening. And we found that there is a change of phase. In that case, liquid is converted into gas, and then it will be whenever it will be attaining saturation temperature, right, and saturation temperature is dependent on the saturated pressure. Saturated temperature will be dependent on the saturated pressure. And we looked at about the saturated liquid line, saturated vapor line, and then we learnt also how to handle the wet mixture or a mixture of vapor and its liquid, right. So, for that we define a term which is known as quality, right, and by knowing the properties at the saturated liquid point and the saturated vapor point, we can evaluate the properties of the mixture, that is liquid and vapor. And let me just ask few questions about what are the implications of the saturated pressure and temperature, right. Can anybody think about what are the things, I mean what are the applications? Implication means what are the applications kind of things one can think of, right. So, we looked at this curve, that is basically saturated temperature will be dependent on, if I look at let us say for a temperature, particular temperature here, and it will be having certain pressure, that is, and it changes, right. So, what is the implication of it, and can I use this some kind of device one can think of, right. For example, I in the last lecture I gave an example of what you call cooking the food. Suppose you are cooking food on the sea level, right, and using the same stove, let us say LPG stove, and you go to the higher altitude, let us say Himalayan region, right. The people do live in that place, right, higher altitude, am I right, and which is quite pleasant, and they do leave that place, particularly in summer, it will be very nice. And if you want to cook food, what problem or you will face? Any idea? What happened? The boiling temperature, because this saturated temperature, which is correspond to the boiling temperature, isn't it? For 1 atmosphere pressure, what we call around something 100 degrees Celsius, the water will start boiling, right. if I go to the higher altitude, let us say 2000 meters, what will be its boiling temperature? Will it be higher or will it be lower? It will be lower. So, that generally per 1000 meter of height, as you go along the altitude, higher altitude, right, then something around 3 degree Celsius difference will be there, right. Suppose you go for 2000 meter higher altitude, then what will be the temperature? Temperature will be something 94 degree Celsius, right. So, if that is the case, then you will take more time for your food to cook. And as you go little more higher altitude, it will be difficult to cook as such, because it will take a lot of time. Of course, if you look at, it takes more time to cook the food at a lower temperature, like if you use your solar cooker, it will be having what you call lower temperatures, it will be attaining the lower temperature. So, therefore, it will take less time, it will take more time for the food to cook, but however, it will be very tasty, because the nutritional values will be remaining intact. So, therefore, that is the one application one can think of, right. So, what else other things comes to your mind? Any idea? For example, like in the last night there was a thunder shower, right. So, what happens to atmospheric pressure at that? I am like after that, not at that time, because at that time it was turmoil, there will be a lot of wind is moving, and then lot of turmoil was there yesterday night. But suppose after that lot of moisture has come into the atmosphere, am I right? Yes or no? Yes or no? Then what happens to the atmospheric pressure? Will it change? What happens to the temperature? Will it change? Change or not? There will be also change in the temperature, but that change in temperature is very, very small, because that depends on the moisture content, right. Let me give you another example, which is just crossing my mind. In IIT Kanpur, we get very hot water even in summer, because what is happening, we are taking the water from a very deep down the earth, right. So, therefore, the water has to travel for a longer length, maybe something around 800, 900 feet kind of things. So, then like you will get water which will be warm, and in summer if you want to take bath in warm water, it is not really very what you call enjoyable, am I right? Of course, I do not know whether you people are feeling or not, but I do feel. But I want to solve the problem. How I am going to solve the problem? That is the question I am asking, because I have solved that problem without expending any energy. Is there any way I can do that? Think about it. So, let us look at what we discussed in the last lecture, right. I will continue on that. So, if you look at, let us say this is my 0.0 megapascal pressure, and this is my almost atmospheric pressure 0.1 megapascal approximately. If you look at, I need to give this heat here, and this I call it as a basically what you call wet mixture. Wet mixture means is a combination of the vapor and its liquid, or liquid and its vapor. But if you look at this length is goes on decreasing, and what is its implication? Its implication that the amount of heat what I will be giving for the lower pressure here, let us say, will be much higher as compared to the latent heat what I will be giving at the higher pressure, because I call it, this is the latent heat portion, like temperature is remaining constant. However, you are adding heat to the your water. Am I right? So, that latent heat goes on decreasing and it becomes 0 at what? At the critical point, right. That you should keep in mind. I thought I did not emphasize in the last lecture this point. I thought let me emphasize again. This is a very important point, right. And as I told in the last lecture, there are lot of efforts are being going on, and it is not that going on alone, and people have already developed superheated boilers, and which is very efficient as compared to the what you call wet mixtures or steam boiler, right. So, now coming back to that, we will dwell little bit upon this what you call the consequence of saturation pressure and temperature, right. Let me just tell you that this temperature, as I told, that saturated temperature will be dependent on pressure and vice versa, right. So, if you look at, like, suppose can I use this thing for producing ice, right, or cooling it, and how we can do? If you look at, like, what I will do, I can go on reducing the pressure, right. When I am reducing, let us say start, like if I am go on reducing the pressure from 100 kPa, almost atmospheric pressure, and what will happen? Temperature will be remaining constant, right. But after, when I am reducing the pressure, then it start lowering the temperature, and at 0.61 kilopascal, the what you call, it will attain the 0 degree Celsius, and you can get the ice being formed. And this kind of cooling is known as vacuum cooling, right. And it is, let me tell you, it is quite costly than that of making other refrigeration and other kind of wet cooling, right. This is also the what you call vacuum cooling. But however, it will be very important for preservation of some certain kind of foods, like particularly the vegetables which will be having what you call higher surface area per unit mass, let us say lettuce or spinach, right. So, those will be can be cooled very easily, whereas if you put tomatoes and other things which is having lower surface area per unit mass, then or cucumber, tomato or cucumber, any other kind of material vegetable, then it will be spoil itself. So, therefore, this is having lot of applications as such in the things, but particularly in the food processing industries and other places, but it is a very costly affairs to do that. And this was done basically long time back, what you call by Dr. William Cullen in 1775, and he had made some ice by evacuating the air space in a water tank. If you look at, I do dabble in some kind of ancient science, ancient Indian science and technology, and I also learned that people were in this country were making ice, right, and without your refrigeration systems, right, how they were making, that was an interesting thing. And if some of you are interested, I can discuss that later on. So, this is one of the application one can think of, and let us look at, there is another application I would like to discuss, that is, suppose you want to keep a test chamber at a very low temperature, like then what we will have to do? We will have to use the liquid nitrogen, right, and we can have a chamber here, right, where it will be insulated properly, and this is liquid nitrogen at minus 19 degrees Celsius and ambient temperature, let us say 25 degrees Celsius. I want to keep this chamber at a constant, which will be test chamber, you can say that at minus 19 degrees Celsius. So, if I want to maintain that, what I will have to do, right? The best way one can think of doing, without intuitively, that I should close this, there is a vent here, right. It could, if you want to design, you will say, look, I will keep this vent closed, or this is a closed chamber I will take, and then put this thing nitrogen, liquid nitrogen, on the top of it I will put this test chamber and close. But however, if I want to keep at a constant temperature of minus 196, then I will have to give this vent. Why it is so? What is the reason? Why should I give a vent? Ideally, one should close it, so that no it will be insulated properly, and then no heat will transfer, so that you will keep the temperature. But if I will close this vent here, what will happen? What will happen? Is actually, if you look at this portion is its vapor, that pressure will go on increasing, because whatever the insulation you do, there will be some heat leakage. Okay. So, then it will start boiling and the pressure will go up, and then the saturated temperature at which the liquid nitrogen is converted into vapor will be changing. So, therefore, you cannot keep it at a constant temperature. So, therefore, you will have to give that things, and so that is therefore, you will have to use the things, the various concepts and knowledge of thermodynamics while designing a system. And you might be knowing, like nowadays you people are more worried about your faces and other things to keep your this thing, you can use also liquid nitrogen as a what you call substance to be remove some of the extra growth what you may have. What you will do, you will take a swab, dip into liquid nitrogen and just put it here in on your face, and then what happened, that portion which is protrusion coming out of that will be freeze, and then you will get the blood circulations, other things, and then that will be removed very easily. So, your face became very, if it is rough, it became very smooth, right. So, this is the cosmetics what people are used. So, this again is a science, and if you look at you might be aware, we are having a liquid nitrogen plant, am I right? You are aware that we are having a very big liquid nitrogen plant, and it was recently inaugurated by our director. Of course, we are having earlier, now it is a big plant, and we use liquid nitrogen for our experiments, and then one has to design similar kind of chambers to keep it the carry out experiments. So, there are several consequences of the saturated relations between the saturated temperature and pressure one can think of. That depends on your imagination. I have just given you few glimpses of it. So, what we had done in the till now is that we looked at the temperature and the volume and keeping the pressure constant. Now, we will look at a situation where we will consider the again the piston and cylinder arrangement, and where we will take a water and at 1 megapascals and 150 degrees Celsius, and we will take our, this is our system, and it is, if you look at, it is already loaded with tiny weights. And if I remove this small weight, what will happen to this water which is at 150 degrees Celsius at 1 megapascal? What will happen? if I remove this weight, the pressure will be decreasing, right. If the pressure will decrease, what will happen to the specific volume? It will change, right. It will be basically increasing, and so also there will be decrease in the temperature. Am I right? There will be slight decrease, but if I want to keep the temperature constant, because now we will be considering the isothermal process, right. What we will do? We will have to give some heat. So, that means I will have to supply certain amount of heat to the water. So, the temperature will be remaining constant. In this case, what is happening? The pressure is changing, so also the volume. So, if you look at, if you go on doing that, then what will happen? The pressure is decreasing in this case 1 megapascal, it is earlier, but as you go on removing these weights, that will be pressure will be decreasing. If it will attain 0.4758 megapascals, it is basically 4.75 what? I mean like 4.75 something around atmospheric pressure, 10 times now, right, of this. So, that time the water will start boiling, right. Okay. And if it will start boiling, then what will happen? Then what will happen to its pressure? Will it be decreasing further, or it will be remaining constant? What will happen? Once it start boiling, the temperature will be remaining constant, so also the pressure, right. Yes or no? Because once, if you look at the other things, what we look at is your TV, when the pressure is remaining constant, the temperature is remaining what? Constant when it started boiling, right. So, if you look at, I mean like this thing, that means what I was telling, like let us say I am here at a pressure of let us say 1 megapascals, right, kind of things here at this point, and as it goes on, what you call decreasing the pressure, there is a change in specific volume, but however, this specific volume change is very, very small. So, for example, if I look at here and if I look at this or some point here, this changes is very, very small, this change is very, very small, right. And this is the point, what I call it basically saturated point, and saturated liquid point you can say, and at this point the what will happen? Water will start boiling, isn't it, at this point, and after that this will be liquid and vapor region, right, and where the pressure is remaining constant, and so also already this is a isothermal process what we are considering. So, temperature is remaining constant, but however, there will be rapid change in the specific volume from this point to this point, and as you what you call right, and this point we call it as a saturated vapor point, and this line we call it basically saturated vapor line, and at this point what will happen? All the liquid is converted into vapor, right, and then of course, as you goes on decreasing the pressure, then what will happen that keeping the temperature constant, then it will follow these ways. And you can conduct the similar experiments at a different temperatures, and you will get this point, and then again you can get the critical point where the what you call liquid will directly converted into its vapor. As I told earlier that this point, this line below which we call it as a compressed liquid region, or we call it a subcooled liquid, and here above it is basically vapor region. And if you look at, if we heat further, like kind of thing, this is known as superheated vapor region, and in between these 2 points or these 2 lines rather, saturated liquid line and saturated vapor line, there will be the mixtures which will be having what you call different quality values. As I told, for example, at this point corresponding to quality X is equal to what? Is equal to 1 here, right, and this point the quality, that is the X, is equal to 0, right. So, in between it will be varying between 0 to 1, and by knowing that we can what you call use these properties and evaluate the properties of various thermodynamic properties. I had asked you what is the quality in the at the critical point. If you look at the quality at the critical point, we can really look at it by looking at the basic definition of the quality, and quality is basically V minus V f divided by V z minus V f, the specific volume of the liquid V f, and V g is the specific volume of the gas. At this critical point, if you look at, right, this is basically V f is equal to V z. So, then what will be having quality? At critical point C p, I am saying the X will be infinity. Are you getting or not? Because at the critical point the specific volume for the liquid is equal to the specific volume of the gas. So, therefore, the quality at the critical point will be infinity, and along the saturated liquid line it will be 0, right, each point will be 0, and along the saturated vapor line it will be 1. So, let us look at now a certain situation of constant volume process for a pure substance, right. For example, if I take a certain amount of liquid and certain amount of gas, in this case if you look at here, the liquid is larger quantity, right, yes or no, and the gas is smaller quantities. What is the meaning of this? This will be, if you look at in terms of X, X will be closer to what? 0 or 1? It will be closer to 0. It cannot be 0, it will be definitely greater than 0, right. So, it will be a small value, maybe let us say something 0.1 or 0.2 X will be. And if I will go on heating this, what will happen? What will happen if I will go on heating? Is it like liquid will be converted into gas, or the gas will be converted into liquid? It can happen because we are considering 2 phase only, right. So, what will happen? What will happen to the wet mixtures? Like if you look at quality, what will be happening to the quality? So, for that what we will have to look at? We will have to look at either the PV diagram or the TV diagram, it can be very clear. But for example, like if I am here, let us say I am at this point, right, with this what you call. So, if I am heating it at a constant volume, that means I am moving in this direction, what will happen? Right? I will be getting at this point, whenever it is having pressure, of course, in a constant volume, if I am heating, the pressure will go up, and then I will be going in these directions, and then at certain things I will be getting all the vapors. Right. Similarly, if I will get the other way around, that is very less amount of liquid and more amount of gas, right, which you can think of that you are here in this region, right, you are again going up as you are giving the heat, that means you will be getting basically the vapor. But I can think of another condition where there will be in between, that means you are think of considering a situation where you are thinking of like making this mixture, you start with this mixture here and you will go on, there will be wet mixtures. If you look at the x value will be changing, right. If you look at the x at this point, what it would be? At the critical point, what it would be? At this critical point, what it would be? I mean, like if you look at my x is, in this case, if I x is 1 here, right, and this point it will be 0, and similarly this will be 0 and this will be 1, what will happen at critical point here? So, it is all 0 and this 1. So, it will be basically, if you take this, consider it will be 0, right, all it will be vapor at that point. But if you are here little down at critical point, it will be having infinity. So, therefore, if I consider this thing and if I draw these curves here like that, this is, let us say, what are this line? This line corresponding to constant x quality lines. So, if you look at it will be something 0.1 and then 0.2 or maybe something 0.3, like that it goes on. So, if I look at what is happening here, if I am going, that means my what you call quality is changing, quality is becoming going towards 0, right. Similarly, here, right. So, let us now look at other aspects of that. We have till now looked at two phases, one is liquid and its vapor. Now, we will consider ice, which is at minus 20 degrees Celsius and 0.1 megapascals, right, and in a piston cylinder arrangement, because so that we can keep our pressure remaining constant kind of things, or it can be varied very easily, any one of them can happen. So, that I can have a control over this I can have a system. If I will go on adding heat, what will happen to this ice? What will happen? Ice will be, what happens to the ice temperature? It will go on increasing, that is obvious thing, right. And as a result, the volume increases slightly. Is it the volume will increase or not? What will happen? Because if it is ice, and of course, if it will be what to call converted into liquid, then what will happen? The volume, for the same mass, what will happen to the volume? I think you think about it, you are not thinking. please think about it, what will happen if ice is converted into liquid, what will happen for the same mass about its volume? Volume decreases. Okay. So, then temperature will be goes on increasing and ice will start melting at 0 degree Celsius, and at the melting what will happen? The specific volume of the water is less than ice. So, that what will happen? The ice will be floating, right, and water will be down. This is the beautiful thing special about the water, speciality about the water. So, whatever the living things what we could see because of these properties of the water which has made us to think. In other words, if you consider the ice age, if you believe that there was a ice age and after that all melts, suppose you imagine it could have been other material like another material, most of the material except water which what you call specific volume of its liquid is less than that of the solid, right. Okay. That means, all other matters will be other way around, the specific volume will be of the liquid will be greater than the specific volume of the ice. So, that it will be having higher density, solid will be having higher density than that of the liquid, right. As a result, you imagine it could have been happened for the water, then what it could have happened? Ice could have been on the bottom of the lake or a sea or any other place, Are you getting? Then what could have happened to the living beings? There is a lot of, in your sea, there is a lot of living beings in the beneath that could have died or could have not there. Let me just tell you, it is crossing my mind, the coastal area are in deep trouble because we are dumping a lot of materials and their biological life is affected by that, and we are all connected with the biological life what is there in the sea, right. We should not spoil it. So, coming back to that, that is the beauty, like that has created a life in this beautiful earth because of properties of the water, that is the speciality of the water. So, and that is what I was telling, that is the vital for nature's evolution. This is a very important point, that is vital for nature's evolution, otherwise we could have not been here, right, talking about thermodynamics if we are not evolved out. So, now let us look at another situation. We will consider the same ice start with minus 20 degrees Celsius, and but we have changed the pressure here 0.265, right, and I will go on adding heat. So, what will happen? The temperature definitely will go on increasing, right, but will it converted into the liquid or not? What will happen? Because we have seen that when the pressure is 0.1 megapascals, right, and it was also at minus 20 degrees Celsius, right, and we found that as it goes on, temperature of ice will be go on increasing, and then when it reaches 0 degrees Celsius, it will be converted into the water, right, and then but in this case it does not happen. It the temperature will be goes on increasing, but till it attains the minus 10 degrees Celsius, and ice will be converted directly into vapor, what we call sublimation, right. This is a very interesting phenomena which occurs for others also, other material pure substances, right. So, and if it is vapor has come and I will go on what you call adding heat, what will happen then? Of course, the ice will converted directly into the vapor, then the further heating, this thing, first all the ice will be converted into vapor, then if you go on adding heat, then it will be converted into superheating vapors kind of things. So, let us consider the another situation. Again we will start with the same what you call the temperature ice, that is minus 20 degree Celsius, that means ice is at minus 20 degree Celsius, but the pressure we have changed to 0.6113 kilopascal. Then if I will go on adding heat, what will happen? See, in all this process what we are trying to do, we are trying to keep the pressure constant, like. So, what will happen to the ice? In just now we saw that the ice was converted directly into the vapor. Earlier we have seen ice is converted into liquid, right, when the pressure is changing. Of course, that this temperature of the ice will go on increasing till it attains 0.01 degree Celsius, and ice will be converted into vapor and liquid state, and this we call it the 3-phase equilibrium. That means, all the 3 phases will be at the same point, it will be simultaneously being present. So, this is a very important point. I had emphasized in the last lectures that this triple point was being used as a reference point for the temperature measurements, right, temperature scale, to make it that, because it is invariable. If there is a small change in that temperature, then you will not get 3 phase, immediately, look, that is not accurate. So, therefore, to get a very precise reference point, this is being internationally accepted. So, if you look, as I told that all 3 phases will be remaining at this point, and this is called 3-phase equilibrium. 3 phases are in equilibrium, there is a triple point. And let me emphasize also this point, that no thermodynamic property of the system can be varied independently at this point, at this triple point, right. So, this is a very important point you should keep in mind. And we will stop over here. We have seen these changes and other things, and we will be discussing in the next lecture about the phase diagram, because we have looked at the various phases considering pressure, what you call volume diagram while keeping the temperature constant, and temperature and volume diagram while keeping the pressure constant, like all those things we have seen. But we will have to look at a diagram which will be important, giving all 3 phases, then only we call it as a phase diagram. Now, let me ask a question, then we will stop over, that is, what would be variables in which I can see. For example, I am having 3 variables in this case, pressure, temperature and volume, right. Now, what I should plot, so that I get all the 3 phases together, right. So, we will stop over with this question, we will continue again with the what you call this phase change process in the next lecture. Thank you very much.